Hello everyone. Today we will continue with hemocyanin, the last oxygen binding protein. Take the heading as hemocyanin. Abbreviated as HC. Capital H, small c. Hemocyanin. Right. So what type of protein is it? It is a bimetallic center. It is an oxygen binding protein. Again, reversible oxygen binding protein. Whatever proteins we have seen, let it be hemoglobin or myoglobin, hemerythrin, hemocyanin. All the three, they bind oxygen reversibly. So we call them as reversible oxygen binding proteins. Reversibility is very important for all these proteins. Hemo and myoglobin, they were single-centered, monometallic. Hemerythrin was bimetallic. Hemocyanin is also bimetallic, but this is a copper center. This is a bimetallic copper center. Hemerythrin, it was bimetallic iron center. This one is bimetallic copper center. When I say bimetallic copper center, it is worth mentioning that it is not a cluster. Hemerythrin was also not a cluster, though you had two irons, but there was no direct metal-metal bonding. So we cannot call it as a cluster. Okay? In a similar way, even hemocyanin is not a cluster, but it is a bimetallic center. This is also a non-iron oxygen carrying protein. This carries oxygen. It is a transport protein, but there is no prosthetic group like porphyrin. There is no prosthetic group. Simply there will be a protein backbone. Suppose if copper is present, directly copper is attached to some amino acids or proteinous backbone, but you don't find anything like porphyrin. Okay? So directly iron was attached to some histidines, endogenous bridges. We have seen it in hemerythrin. In hemocyanin, directly the metal copper will be attached to some protein, amino acids, okay, which is a part of protein. So we call it as non-heme because there is no prosthetic group, and non-heme, non-iron oxygen carrying protein is hemocyanin. Non-heme iron protein, non-heme iron protein, hemerythrin. Hemerythrin is a non-heme iron protein. This is a non-heme, non-iron oxygen binding protein. Okay? Where do we find this? Hemoglobin, we find it in snails. Hemoglobin, we find it in vertebrates and very, very few invertebrates. Hemerythrin, it is found in marine invertebrates and a bacteria Methylococcus. Hemocyanin, we say that it is found exclusively in two phyla. Exclusively. You don't find it in any other organism, but exclusively in two phyla. Phyla means it is a group of organisms. It is just a classification of animal kingdom. We call it as phyla. It is found exclusively in two phyla. These two are mollusca and arthropoda. You may just write down this point. HC is found exclusively in two phyla. In two phyla. Phyla is a classification of animal kingdom. exclusively found in two phyla. They are mollusca and arthropoda. Mollusca and arthropoda. You may just take down a few examples for mollusca and arthropoda. Mollusca and arthropoda. You might have seen snails, octopus, lobsters, scorpion. Which blood do you find in them? Blue blood. Okay, write down a point. Cyanos means cyanos means blue. Cyanos means blue. Hemocyanin, it means it was called as blue blood in the beginning, but later on we have understood that heme is not blood. It is a prosthetic group where the metal is surrounded by porphyrin in the case of hemoglobin and myoglobin. Okay, next coming to subunits. How many subunits do you find? Write down. There are several subunits. There are several subunits which are usually found in the multiples of 6. Which are usually found in the multiples of 6. Example: 6, 12, 24, 48, etc. 6, 12, 24, 48, etc. Next, along with this, the other subunits were 2, 10, 20, etc. 2, 10, 20, etc. So anywhere do you find a single subunit? No. So there is no myohemocyanin. There is a myoglobin. Myoglobin is a monomer. Myohemerythrin is a monomer. But in this case you don't find myohemocyanin. It means there is no monomer, but there are several subunits. It is starting from 2, 10, 20. In the beginning they thought it is only multiples of 6, 6, 12, 24, 48 and so on. But later discoveries have also shown that it is not only in multiples of 6, but you can also find it in 2, 10, 20 and so on. But there is no monomer of hemocyanin. Okay, you may note down that point. There is no monomer. There is no monomer for hemocyanin. There is no monomer for hemocyanin. That is myohemocyanin is absent. Myohemocyanin is absent. Just like you have myoglobin, myohemerythrin, there is no myohemocyanin. Okay. So when I say about subunits, what is the weight of subunit? You can see the weight of subunits, it is ranging from 10 kilodalton to anywhere around 50 kilodalton. For hemoglobin we can exactly say that it is 64 kilodalton hemoglobin. Myoglobin it is anywhere around 17 kilodalton. Hemerythrin was 13.5 kilodalton. But this one has a range that depends on the organism. It is ranging from 10 kilodalton, one subunit. It can go up to 50 kilodalton. It means it is a very large protein. Its molecular weight is also very high. So you may just imagine, suppose if there are 48 subunits, each subunit weighing 10 or each subunit weighing 50 kilodalton, the weight of the protein will be very, very high. Okay? So you may just note down that point. The weight of each subunit the weight of each subunit range from 10 kilodalton to 50 kilodalton. The range of each subunit the weight of each subunit range from 10 kilodalton to 50 kilodalton. So very high molecular weight. Okay. So this is about the introduction. The very first isolation of this protein, they have done it from snails. You might have seen snails. And from these snails, they used to take the blood. With the help of that blood, they used to write. So that was used as a pigment, just for writing, ink. Now we are using several inks, but in olden days, they used to kill these snails. They used to take their blood and they used to write. So you might have heard about a color called as royal blue. In blue, there is a royal blue. That will be a little bit different color. It is just like a Prussian blue. It is not a regular blue. We call it as a royal blue. So usually this color will be like that. That is the reason it is also called as a royal blue. Royal blue means kings and queens, they used to use that color. So it is called as a royal blue. Okay. Now let us begin with deoxy and oxy, and we'll take geometrical aspects, magnetic and electronic aspects. Begin with deoxyhemocyanin. Deoxyhemocyanin. This is also a very simple protein like hemerythrin. Deoxyhemocyanin. This histidine is connected to protein part. So all this is like a big protein backbone. In this you have a copper. Each copper is present in +1 oxidation state. Each copper is present in +1 oxidation state. Okay. Can you look at the geometry? 90% of the books you don't find this geometry, but this is the correct geometry. Around each copper you find a trigonal pyramidal type of a geometry. It is not a trigonal planar, it is a trigonal pyramidal. This is not straight bond, it is just like bent, bent and bent. So it is like ammonia, if you are able to imagine. Nitrogen, hydrogen, hydrogen and hydrogen. Around each copper there is a trigonal pyramidal geometry. And how are the two trigonal pyramidals? They are like staggered to one another. They are not eclipsed. If at all you are imagining a triangle, in this triangle corner is above. Okay? But in this triangle that corner is below. Are you able to imagine? If I connect these three nitrogens, it is forming a triangle. I connect these three nitrogens, it is forming a triangle. The two triangles are staggered to one another. They are not eclipsed. Okay, first point. Second, out of the three bonds, one bond is longer. The other two bonds are shorter. Did you notice? I have drawn this long, I have drawn this short. Exactly opposite, this is long, but these two are short. So out of three bonds, one bond is long, the other two bonds are short. Coordination number around each copper is 3. Nitrogen, nitrogen and nitrogen coming from histidine. Okay. So both coppers are similar. They are just like identical, not like hemerythrin where coordination number is changing. But in this case coordination number is 3. Coordination geometry is trigonal, pyramidal, and in trigonal pyramidal one bond is long, two bonds are shorter. Two trigonal pyramidals are, they are staggered to one another. Okay. Don't put any metal-metal bond between the two coppers. It is not a cluster. It is simply embedded into a protein. All if this is protein, in that protein two coppers are present attached to the histidine nitrogen, but there is no direct bonding between them. Oxidation state of copper is 1. So if I say copper is in +1 oxidation state, what is the D configuration? D10. D10 means how many unpaired electrons? 0 unpaired electrons. So magnetic property, it is diamagnetic. Deoxyhemocyanin is diamagnetic. There are no unpaired electrons, no DD transitions. So you don't find any color. Even there is no possibility for ILCT, intraligand charge transfer transitions, because you don't find any porphyrin type of ligands. There is no LMCT, there are no other ligands. Okay, so deoxyhemocyanin is colorless, deoxyhemocyanin is diamagnetic. Deoxyhemocyanin, each copper has trigonal pyramidal geometry with coordination number of 3, where one bond is longer, two bonds are shorter. Okay, let us write about the points. First, geometrical aspects. Geometrical aspects. Geometrical aspects. Each copper has trigonal pyramidal geometry. Each copper has trigonal pyramidal geometry with coordination number 3. Each copper has trigonal pyramidal geometry with coordination number 3. Next, the coordinating ligands are, you may write down nitrogen of histidine, all the 3. All the 3 are nitrogen coming from histidine. Nitrogen of histidine. Next, out of 3 bonds, one is long and 2 are short. Out of 3 bonds, one is long and 2 are short. Next, the two trigonal pyramids in bracket, trigonal pyramids of what? Ligands. The two trigonal pyramids of the ligands, in bracket you put of the ligands. The two trigonal pyramids are staggered to one another. The two trigonal pyramids are staggered to one another. Okay, that is about geometrical aspects. Next, magnetic aspect. Magnetic aspect. Deoxy-HC is diamagnetic. Deoxy-HC is diamagnetic with copper 1 D10 configuration. With copper 1 D10 configuration. With copper 1 D10 configuration. Next, electronic aspects. Electronic aspects. Deoxy-HC is colorless. Deoxy-HC is colorless. Okay, so that completes deoxyhemocyanin. Next one is oxyhemocyanin. Oxyhemocyanin. Deoxy is completed. Let us begin with oxyhemocyanin. First I'll explain the structure, then you can draw it. Previously you have seen a trigonal pyramidal, two trigonal pyramids were staggered to one another. In this case, around each copper there is a square pyramid geometry, square pyramid. There you have seen a long bond and two short bonds. One long bond and two short bonds. Now that long bond becomes the apical bond of a square pyramid. If this is a square pyramid, this is the longest bond. Previously we have seen one long and two short. So these are the two short and this is one long. Along with that you also have two more ligands. They are coming from oxygen. Okay, these two oxygens are bridging two copper metals. Likewise, you have another square pyramid, both square pyramids like anti to one another. Previously it was like staggered to one another or anti. In this case also two square pyramids are anti to one another. Okay. What is the bonding mode of dioxygen? Side-on bridging. It is side-on bridging. Suppose if I ask you in hapticity, neta 1, neta 2, what is the hapticity? Neta 2, neta 2. Okay, it is neta 2 hapticity. Right? Next. Each copper was found to be present in +2 oxidation state. Each copper, previously from copper 1 and copper 1, it is now coming into copper 2 and copper 2. The distance between the two coppers will decrease. Just as in hemerythrin we have seen the distance between the two irons drop, here also the distance between the two coppers will decrease because it is entering into copper 2. Copper 2 is D9 and D9 has one unpaired electron. Since they are very close, they behave like almost opposite we can take. So there will be a very strong anti-ferromagnetic coupling, and due to this strong anti-ferromagnetic coupling, this will become diamagnetic. So though there are two unpaired electrons, oxyhemocyanin is diamagnetic. Okay. Deoxyhemocyanin, it is diamagnetic. Oxyhemocyanin, it is also diamagnetic, but in hemoglobin hemerythrin it was different. Para and dia. In this case both are dia and dia. Because it is copper 10, it was dia, D10. Next one, copper 2, D9, one unpaired electron. But there is a strong anti-ferromagnetic coupling where the two electrons behave like they are paired up. Truly they are not pairing up in a single orbital, but they behave like they are paired up. Therefore you will be getting diamagnetism. That is about magnetic aspect, geometry and magnetic aspect. Coming to the electronic aspect, what is the color? Cyanos means blue. Hemocyanin is a blue blood. We call it as a blue blood. So the color is blue, and the reason for color? It is LMCT. LMCT from O2 2 minus into copper 2. So here you find O2 is converting into O2 2 minus. In hemoglobin and myoglobin, O2 is converting into O2 minus. Hemerythrin, O2 is converting into O2 2 minus. Hemocyanin also it is peroxo, O2 2 minus. So there is a charge transfer transition from the ligand to the metal. You get two peaks, 450, 476, two peaks. In where did you find 450 and 476? Hemoglobin. 350, 455. Hemerythrin. 350 but 550 in the case of hemocyanin. So there is a change of one peak. The remaining peak is almost same, 350. In hemerythrin you find 350 and hemerythrin 455, and the color was purple or violet pink. But in this case you are getting 350, along with that you are getting 550, and that is giving you blue color. Okay, so these are the points. And one final question. I am saying that it is a peroxo form. What is my confirmation? Stretching frequency. How much could it be? Anywhere around 800 to 900. The value they found was 750 wave numbers. So it is very close to 800. What is my confirmation? Dioxo is in the peroxo form. How do I get? With spectroscopy? IR. Or I can also club IR and Raman. We say IR stretching frequency, but I directly take oxygen. We know that oxygen has a center of symmetry, so it will not be IR active. But whenever it binds to metal, center of inversion is lost, then it can become IR active. So generally these are IR active or Raman active. We generally speak of both stretching frequency, IR and Raman. If it is active in IR, it may not be active in Raman. If it is active in Raman, it may not be active in IR. Some, they are active in both, some are inactive in both. Okay, that depends. It generally comes in symmetry and group theory, which is not needed now. But you can just understand stretching frequency comes from either IR or resonance Raman spectroscopy. 750, what does it indicate? Usually what is the range that I have given you? 800 to 900. But what is the range you are saying here? It is 750 only. It is not even coming to 800. Not even coming to 800. What is the meaning of it? Just an understanding question. If I take a regular dioxygen, I am just taking dioxygen. Dioxygen has 2 bonds. I am giving some radiation. If I want to stretch dioxygen, how much energy is needed? 1,555 wave numbers of energy is needed to stretch dioxygen because it is a double bond. From double bond, whenever it is converting into superoxo form, what will be the bond order? Bond order will be 1.5. It means to stretch them, how many bonds are there? Only 1.5. For stretching 2 bonds, if I need 1,555 wave number, for stretching 1.5 bond, do I require more energy or less? Less. It was anywhere around 1100 wave numbers. So I had to put lesser energy. Now if it is a peroxo form, how much is the bond order? Only 1. So I have to stretch how many bonds? Only 1 bond. I require still lesser energy. For double bond it was almost 1,555. For single bond it is anywhere around 800, half of the energy that I have to utilize to stretch it. But in this case it is 750. What does it indicate? It means bond is still weaker. Did you get the point? Stretching frequency is dropping, it means bond order is dropping. Right? For statistics purpose we say bond order 1, bond order 2, but electron is like a wave. It is like a wave. So lesser than 1 bond order is found, therefore you are getting lesser than 800 value, it is 750. What could be the reason for such a low stretching frequency? Already we have given range should be around 800 to 900 for peroxo. It is still dropping the range. It means it is lesser than a peroxo stretching frequency. How do you explain this? Simple explanation here. In hemerythrin, how many irons did the oxygen bound with? Only 1 iron. But in this case, the oxygen is bound with 2 coppers. And both coppers are giving electron density. There also 2 irons were giving electron density, but indirectly. 1 iron was giving indirectly. We said oxidative addition. In this case, dioxygen is directly bound with 2 metals. Both metals are pouring electron density into dioxygen. So dioxygen actually will have double bond. Dioxygen will actually have double bond. But whenever it is binding to metal, slowly electron density will flow, bond order will decrease. The bond order decreases to such an extent it becomes superoxo and later peroxo. Within that peroxo also, electron density will flow to a greater extent. Reason is favorable orbital interactions. This is favorable orbital interactions, that bonding. So due to that, more electron density will flow from copper. So this bond will be much thinner. It will be much thinner. Okay? But nature protects it in such a beautiful way, more electron density will not flow. It will stop. Because if more electron density flow, even this bond will break. If this bond will break, reversibility is lost. Once oxygen is like this, reversibility is lost. Almost the organism is dead. That should not happen. So how much ever electron density flow, nature will always put a limit. That limit is not crossing a certain bond order. So the last is 750 wave numbers. Okay? If any understanding question appears, usually the range of peroxo is from 800 to 900. But in hemocyanin, why do you find it as 750? The simplest answer is side-on bridging, where 2 metals are pouring electron density into the ligand, and therefore stretching frequency is dropping. Okay, that is an understanding part. Now you can draw this diagram. This I am just drawing it thin because it is not even a full single bond. It will be little lesser than a single bond. One bond you put it longer, the 2 bonds are shorter. 2 bonds are shorter, 1 bond is longer. Geometry, magnetic and electronic aspects. Shall I start? You are drawing it. Try to remember the values of stretching frequency for hemoglobin, myoglobin. Both hemoglobin and myoglobin are similar, hemerythrin and hemocyanin. Once I complete hemocyanin, what you can do after going home is, you may just take a chart, classify in the sense you just put a table, one table related to hemoglobin, main heading, myoglobin, hemerythrin, hemocyanin. Whatever characters that are common, similar or different, you just write down that parameter. For example, I am just telling number of metals. Hemoglobin, 1 metal, monometallic center. Subunits are 4, but each subunit has only 1 metal. Myoglobin 1, hemerythrin 2, hemocyanin 2. Next, heme protein, non-heme protein, non-heme protein. Heme iron, non-heme, non-iron. It is copper protein. Stretching frequency of dioxygen. In hemoglobin and myoglobin, it was 1050. Both will be common for myo. Next case, it was 843. In this case, it is 750. Then peaks. How many peaks appear? 2 peaks. You just put the values. 555 and 400 for deoxyhemoglobin. Likewise, all the peaks you put. The last one that I have shown is 350, 550. 350, 450 for hemerythrin. So when you put all those values in a single page, you can have the comparison of hemoglobin, hemerythrin, hemocyanin in a single page. Immediately you can check all the data, which is paramagnetic, diamagnetic. Deoxyhemoglobin para, oxyhemoglobin is dia due to antiferro. Again hemerythrin para, dia due to antiferro. In this case dia and dia, but dia due to antiferro. So these are the details that you are going to write. That will be easy for you. All oxygen binding proteins will be in a single page. Completed? Note down the points. First, geometrical aspects. Each copper has a square pyramid environment. Each copper has square pyramid environment with coordination number of 5. Next, the apical bond is longer. The apical, APICAL, the apical bond is longer, whereas equatorial bonds are shorter. Next point, the two square pyramids are anti to one another. Next, each copper is in +1 oxidation state. Each copper is in +1 oxidation state. +1. Deoxy. I am giving about oxy. Yeah, oxy. Okay. Oxy is +2. Deoxy we have completed. +2 oxidation state. Okay, so that is about geometrical aspects. Then you write down the magnetic aspects. Copper to D9 has one unpaired electron. copper 2 D9 has one unpaired electron, but due to a very strong anti-ferromagnetic coupling, oxyhemocyanin is diamagnetic. Oxyhemocyanin is diamagnetic. Oxyhemocyanin is diamagnetic. Okay, that is about magnetic aspect. The last one, electronic aspect. Oxyhemocyanin is blue colored. Oxyhemocyanin is blue colored. The color is due to LMCT. The color is due to LMCT. You can just write this. LMCT O2 2 minus into copper 2. That LMCT is from O2 2 minus, peroxo into copper 2. Peroxo into copper 2. Next, two peaks appear in the absorption spectrum. Two peaks appear in the absorption spectrum at 350 and 550 nanometer. Two peaks appear in the absorption spectrum at 350 and 550 nanometer. 350 and 550 nanometer. Okay, just write a question. What is the dioxoform? What is the dioxoform in hemocyanin? What is the dioxoform in hemocyanin? So which dioxo? Is it simple dioxo? Is it superoxo? Is it peroxo? Peroxo. Answer is peroxoform. Peroxoform with a stretching frequency. Peroxoform with a stretching frequency of 750 wave numbers. With a stretching frequency of 750 wave numbers. If you want, you can just write 2 points why the stretching frequency is lesser than expected. This stretching frequency you may just write nu. Every time you need not put stretching frequency, just write nu. The stretching frequency of O2 is very less than expected, than expected, which is due to strong orbital overlapping interactions. Between metal and ligand. Strong orbital overlapping interactions between the metal and ligand. Next important point, the bonding mode of O2. Whenever I say O2, that O2 you have to imagine to be a peroxo. because that O2 is converting into peroxo. O2 will convert into superoxo and so on. The bonding mode of O2 is side-on bridging. The bonding mode of O2 is side-on bridging. Side-on bridging. Okay. Now look at the board finally. So which one is the oxy-hemocyanin? Side-on bridging. Last one. Then what is the first one? Suppose I am taking a deoxyhemocyanin. In this deoxyhemocyanin there are two copper centers. Each copper has got a unpaired electron. Usually these two unpaired electrons can have a same spin, or they may have a opposite spin also. But usually whenever they have a same spin, oxygen slowly comes. This is how the bonding is explained. Oxygen slowly comes. That oxygen is establishing a bond with two coppers. Still the two electrons are with same spin. This type of bonding we call it as neta 1, neta 1. Okay, what is the bonding mode of dioxygen? This is like a neta 1 and neta 1. It is only like end-on bridging. But slowly from here it will be coming to this stage where one is side-on, one is end-on. So this particular one we call it as a neta 1, neta 2. This is neta 2, this is neta 1, or I may also put here and here I may have. No problem. But one is 1, one is 2. That is the meaning of it. So neta 1, neta 2. Slowly from neta 1, neta 1, it is moving to neta 1, neta 2. In this case, oxygen attached to two metals, neta 2. Second oxygen also attached to two metals, neta 2. But neta 2, both electrons may have same spin. Finally, there will be a process within inside. That process will make the two electrons to have a opposite spin. Okay? So that is the last process, and after that last process, this ligand will be shifting into the center. Did you see the transition? Slowly the ligand has come, the ligand is bonding. Now slowly the ligand has bind like this, and then it is entering into the center. So that is how slowly a transition is occurring, and finally there will be antiferromagnetic coupling at this point. This we call it as a neta 2, neta 2. So this is the last one. This is also neta 2, but still antiferromagnetic coupling is not seen. In the last stage, antiferromagnetic coupling will also occur. You may just roughly draw them. Antiferromagnetic coupling can occur in the last stage. That is generally called as super exchange stabilization. The last one, we call it as super exchange stabilization. The process is called as super exchange. But all those physical terminology is not needed. What we have to remember is neta 1, or is it neta 1, neta 2, and so on. For all examination purposes, what is the hapticity of dioxygen? Last one, neta 2. This is just an explanation how the ligand is coming, how it is slowly adding to the two coppers. That is the explanation. But never write neta 1. It is just like a transition state. The last one is a neta 2. Antiferromagnetic coupling, super exchange stabilization we call it as. Last one step is called as super exchange stabilization. So with this we have completed oxygen binding proteins. For JL people, it is that unit is done. Oxygen binding proteins, hemoglobin, myoglobin, hemerythrin and hemocyanin. Very important topic, 100% questions has to appear from this unit. You may not believe, in one of the CSIR exams, just from bio-inorganic chemistry, they have asked 16 marks. 16 marks have come from this single unit, bio-inorganic chemistry. But at CSIR level, you have to also study redox proteins, not just oxygen binding proteins, you have to also study enzymes and also redox proteins, cupridoxins, pyridoxins, so on. Finished? We just wait a minute, I'll just come.